Hi there. So I'm Julie. I'm from NASA. I'm the deputy lead for the ISRU system capability. So today, I think this first panel is a good way to frame the discussion, especially after those workshops we've just went through where we're trying to kind of define an LPG. And maybe this will help settle that and talking a little bit more about what capabilities and features that such lunar proving grounds might need. And maybe that'll help us define how a lunar proving ground might be distinct from those facilities like TVAC chambers or field test sites, and see how it goes. So we've got a distinguished panel right here to talk to them. So we're going to go through, each person has about 10 minutes to go through and give you an overview of their background and what they have to offer, and then start writing down your questions or putting them on Slido. And are we going to use Slido for this?
Yes, thank you for the reminder. So, any questions that you have for any of the panelists, they can go into Slido. It's the exact same link from this morning, and we'll have a nice big hefty Q&A session after this that will make sure to hit all of those questions. So put them in Slido, please.
Excellent. Okay, let's get started. We're going to start off with Paul Van Sousant from Michigan Tech.
All right, thanks, Julie. All right, slides are up. Excellent. All right, so my name is Paul Van Sousant. I'm assistant professor at Michigan Technological University, and I'm the founder of the Planetary Surface Technology Development Lab at Michigan Tech. So the reason we're here today is Lunar Proving Grounds, and so we've talked a little bit about what a proving grounds could be. Now, my proposal is to not call it the Lunar Proving Grounds, but calling it the Lunar Proving Grounds Consortium or something like that, because it's not just the proving grounds. There's vacuum chambers, there's field tests, other things that come into play. And so there's been some miscommunication on that, I think. And so having a consortium that does a lot of different tests, I think, is important. We're not looking for one thing that does everything. But what does it need to do? Well, I think the goal is to test and help develop full-size lunar subsystems at mission scale for long duration. And this is something that was not the case for Apollo because we were only there for a couple of days. So now we're talking long duration. I think that's the key difference in the tests that we need to do. And there's many different facets that have already sort of been mentioned that need to be tested. And so there's a whole list of here. Now, besides the technical aspects, there are also other aspects that are important, such as public relations, education, and then sometimes what I like to call out-of-sight testing, where you want to break things and you don't necessarily want that to happen on camera or in the public eye. So very important aspects. Now, the question is, what kind of scale does this kind of facility need to have? And if you look at these kind of NASA analysis, and this is sort of two different subsections that I just copied here from NASA. One is excavation, the other one is construction for ISRU. And so both of these are sort of the work area I do. I know there's many other areas, but this is a very important one to me, and so that's why I picked this as just an example. And you see in these red boxes kind of what the scale is that we're looking at. Now, another thing that's really important is travel perspective. When we talk about things like ISRU and mining water or other things on the moon, we need to gather large quantities of material to then process them. And we've done some analyses. In this particular case, it was for Mars, but the same analysis is perfectly valid for the moon. If you want to gather a certain quantity of material with a certain amount of robots at a certain distance, you need to drive and make a certain number of trips, and so you drive a certain distance. And so when you can see in that red column is hundreds to thousands of kilometers that you need to drive. Now, on other planets, the furthest any rover has so far driven is about 50 kilometers, give or take, and that was in 10 years. We're talking about doing thousands of kilometers every year, so very different kind of requirements. So how do you test for these kinds of things? So there's a design and a testing paradigm shift that needs to happen, as Rob Mueller likes to call it, blue-collar robots. And so the question is what size you need and all these kinds of things. So how do you test for that kind of use of systems that we have never really done? NASA has never developed these kinds of robots yet. And so how do we design, develop, and then test them? Now, one thing that always gets forgotten is rocks. So we always talk about simulants, but there's also lots of rocks. And so we have to be able to test with those as well. Very important aspects. Ooh. There we go. Apparently it's a high memory slide. All right, so just to give you an example, this is something we actually did last week at Michigan Tech. So we are part of the Break the Ice Challenge, and so to do that, we need to build a test site to excavate 12,000 kilograms of cemented material in 15 days. That's something that's about, 2 cement trucks full of material. Really not that much when you think about it. But to design and build a facility to do this, we had to do this outside, but 15 days with a robot that's not necessarily rain-proof. How do you deal with that? So we need to set up tents, we need to make all these forms, we have to pour the concrete. Lots of logistics come into play when you want to do a test like that. And then in our case, the traverse track that you see there is actually lunar simulant, which we really don't want to get wet at all. And so that has to be protected from the weather as well. And so here you can see something we did last week. We did this in 2 days. We built this whole site. We leveled it. We graded it. We dug a hole for the deep concrete portion. We built the tent. We put up the formwork for the concrete to put in, and then we poured the concrete. And now it has to harden for 28 days. In the meantime, the tent has to stay there, has to be protected, all that kind of stuff. So this is a really small scale test, all right? So we're talking about building a lunar base and all that sort of stuff. That's a much larger scale than this. This was 10 students and a lot of heavy equipment doing this fairly quickly. But that's also easy because we have it all available right there. So it was pretty easy to do, yet not easy to plan for and execute. So when you make a selection for proving grounds, you need to know what questions you're trying to answer, all right? And so if you're going to select what kind of proving grounds we need, you need to figure out first what scale you need. Now, these numbers that are shown here are from these earlier graphs, and so talking 50-meter diameter landing pads, thousands of metric tons a year of excavation. Like I was just saying, 12,000 kilograms, but now that's 12 metric tons, and we're talking about thousands of metric tons. So how many trucks of material are we talking about? A lot. Right, so all of these different pieces are important to figure out what a proving ground actually would have to be able to do. Right? So do you need indoor controlled situation, or can you go in the field somewhere to a desert or maybe a frozen Antarctic site and you can do your testing there? Well, it depends on what you're trying to test. Right? I think there is a need for indoor controlled facilities that can do certain things, but only part of the test. Now, what capabilities do we need? Well, if you're talking about large landscape creation, different customers might need different landscapes, so you need to be able to manipulate, mix, prepare hundreds of tons of regolith. How do you do that? All right? So you need large earth moving equipment, etc. And operators to do that, skilled people to do these kinds of things. Well, and there's a whole list of things that I've come up with, right? It's just here for you to read. But keep in mind, it's not just capabilities, you also need the expertise. If you're going to design and test your tires, you need a tire testing rig, but you also need somebody who knows how to use that test rig and to interpret the data and maybe help you design things, okay? So the expertise you need to do these are also part of a Lunar Proving Ground facility. It's not just the building itself. Now, what kind of strategy should we then apply? And we've already talked a little bit about this morning. But first, we have to understand the existing facilities and the capabilities. And what can we already do? Because it would be silly to duplicate capabilities unless there is still more demand than the existing facilities can already meet. And then, of course, where are they located? Is that a good place or not to build or expand? And then, based on all that, well, what do we still need that doesn't exist, right? What capabilities are missing? Medium and large facilities especially. Even though there's quite a few small facilities, they're still not necessarily fully utilized. Then, in my humble opinion, because that's kind of the area I work in, we need large-scale regolith simulant testing. Very important that we don't have that capability. Some of the work you see here is just 1 metric ton of lunar simulant, 1 to 2 metric tons of lunar simulant. It takes us a week to prep for it, a whole thing, and then reset the test bed and everything like that. It takes a long time. There's a lot of logistics involved with that. Now, another thing is easy and affordable access, not just by the government, right? So NASA facilities are great, but they're hard to access, and they're expensive and to use as well. So it's good if a Lunar Proving Grounds could be easily accessible by other parties, all right? And to keep the cost low and leverage existing expertise, I think a co-location would be important for some of these facilities, right? If you want to build something that needs to move large quantities of regolith, well, maybe we should put it next to a facility that already does that, but maybe for earth use. So the equipment and the operators and the expertise is already there to do that. And in that case, the lunar environments as such just becomes another amount of dirt to move in a way, different kind of dirt. Now, in the end, I think what we are going to get is a consortium, right? Various locations, facilities, expertise, things that collaborate together and have an information exchange so we can together develop this kind of thing. But it does require things like intellectual property protection as well. And there are existing consortia that do exactly this for other fields. So with that, I can open it up, I guess, to the next speaker, and I will save questions for afterwards. So thank you very much.
I'll wait for the clock to set. Or I'll take a few extra minutes, seconds. Yes. Yep. So my name is, I go by Miranda. My name is Miranda Cooter. I'm going to be presenting these slides, although this is the work of a panel that I'm on for the NESC. My background is system safety, so that's kind of shades whatever I talk about, although I consider myself a system engineer. So this panel we've been talking about, so kind of going to go from the broad that Paul discussed to a more specific parameter to consider in the Lunar Proving Ground, and that is the visual experience. This is during EVA, but you could apply some of this to cameras as well at the Lunar South Pole, which is where we're planning to go. I do have other panel member is here today, and he's over there, Tom Walters. So if you have other questions, you can ask him as well. Next slide, please. Oh, I have a clicker. Okay, there we go. So these are the potential landing sites for Artemis 3, and it kind of looks at the impact on human vision. So you probably know, everybody here probably knows, it's not going to get much above 7 degrees. And it's going to be very variable. That means really long shadows, very bright, lots of glare. So it will affect the vision a lot more than you would have seen for Apollo, because Apollo was, of course, at the equator with 100% sunlight during their missions. So from a system safety standpoint, that means that you're going to be walking around, in darkness or with a lot of glare. You got to be able to see where you're going. You got to be able to manage the tools. You have to be able to see what you're doing both close up and at a bigger distance. So that affects EVA tasks, and it will also affect any cameras. So this is kind of an illustration of of how difficult it might be able to see. Although this simulation is from on orbit, it's based on LRO data, the Lunar Reconnaissance Orbiter data. So they're at 84 degrees of south latitude. This gives you some more numbers. And as I said before, the shadows are really, really long. And with a 6-day mission, you're going to see change in the lighting when you go out. So if you go behind like a 100-foot structure, you won't be able to see it. It'll be dark, and then you'll come out in the light and you'll have a ton of glare. So you have to manage that. We'll go on to the next slide. So we've been looking a lot at the Apollo experience with lighting, and even they had trouble with the sun. This picture is from Apollo 12, and where you probably may already know that it burned out the camera sensor for color in Apollo 12, and so all the pictures were black and white as a result. This is this close, this is at 7.5 degrees, so it's a little bit higher than the maximum you'll see at the South Pole. And it did affect their task performance quite a bit. They, the color camera was, like I said, was disabled. The sun's brightness was commented on several times, and there's a quote. And they waited, they waited until they got into shadow because as he said, I can't see what I'm doing. So that's a strong consideration for what needs to happen with any kind of lunar proving ground where you're going to use cameras or, think about EVA interaction with vehicles or with tools. The surface features, right now we have knowledge of the surface features from a distance, from LRO data, and that which has 5-meter resolution. But when you're looking at something, on the ground level, you're going to see something different than you see from on orbit. So in trying to make a simulation of that, or trying to make that is an important piece of a lunar proving ground, and also your ability to see, if you're coming up on a crater, you'll see that it's a raised surface, but you don't know what's on the other side necessarily. So you'll have to have some kind of way of navigating that. And the sunlight is going to cause enough glare that will be difficult. There's a lot more craters at the lunar South Pole than there were at the Apollo sites because it's on the South Pole, and it's a different part of the moon, different geography. And while rocks are relatively rare, we do expect them to affect your vision because they reflect, because when they are hit, they can cause a glass reflection onto your vision. So we did look deeply at human vision. So there's a lot of backup slides that I provided with this presentation because this presentation was based on a much longer presentation and a much longer study. So you'll find in the backup slides a lot more backing, more detailed information about human vision and about more specifics about this study that we've been doing. So one thing to always keep in mind is that human vision is adapted to Earth, right? So it takes you 30 minutes to adapt to full darkness. It takes 10 minutes to be able to see. So that has to be considered whenever you're working on anything to do with people, or even the cameras. Cameras can be designed around that, but cameras are very specific. Human vision is what it is, but human vision is much more dynamic. So you have to keep that in mind. The sun will always be close to the horizon, like I said. So the lunar surface operations weren't conducted in those circumstances. In fact, they didn't have any lights at all and on their suits in Apollo. So you have to consider that when you're looking at any kind of lunar proving ground, that you're going to need lights, and the lights should be coordinated. In other words, you don't want you don't want a light to affect the ability of something else that's in the area to see as well. So you have to consider that when you're building tools. And shadows, you'll have to have light for the shadows, as obviously, but the bigger consideration really is the glare. I mean, even as I'm standing here, I see, a ton of glare from these lights, but it's going to be much, much worse. And there's been some work to quantify that, and some of that information is in the backup slides. So, in summary, these regions will be a lot more challenging, and they should definitely be considered whenever you're building the lunar proving grounds. So I gave somebody else some extra minutes.
I guess I can start by complimenting the organization of the panel, because that was a good lead-in. I'm going to be talking a lot about communications, which is not exactly illumination, but it's all electromagnetic radiation, right? So a lot of the same phenomenology is important to us. So I'm Mike Zemba. I'm from NASA Glenn Research Center. I am the lead for communications and navigation on the Lunar Architecture team, which is part of the Moon to Mars program within NASA that we heard about earlier in the keynote. I'm also the principal investigator for a project called Lunar LTE Studies, or Lunar Lights, which is developing modeling, simulation, and emulation capability specifically for communications platforms and specifically for investigating the potential use of 3GPP or 4G and 5G technologies like we are so accustomed to here on Earth, and potentially deploying those within our lunar communications architecture. So I thought to potentially wake everyone up after lunch, I would start with a game. So my title slide, as you can probably guess, is a picture of the lunar surface. And the question is, does anyone know what that feature is or how tall it is? Any ideas? Yeah, we have some Apollo historians or lunar geologists, I don't know. But yes, it is Mons Hadley. So this was Apollo 15, and Mons Hadley, from this perspective, is about 20 kilometers away, and it is 4.5 kilometers base to peak. So to compare that to something with terrestrial experience, that is taller than K2. So you're looking at something that is comparable to the largest mountains on Earth, but you can't really get a sense of that on the moon because you have no sense of scale. There's no atmosphere causing absorption of the light to give you some gradual color changes. So the reason I wanted to include that was just to start off with a sense that we can't always trust our intuition when it comes to the moon, right? And that's why we need lunar proving grounds. We need to build these test capabilities that factor in everything that we know to the best of our current understanding to be able to test things and not have to rely on our intuition, because it's difficult to decide how things are going to perform on the moon, whether it's planning a hike up Mons Hadley or deciding where to put your antenna or your Wi-Fi router and things of that nature. So I'll skip through the agenda to try and save some time. I think my slides are probably a little bit longer than I should have. But so another real quick justification for proving grounds. I know I don't need to sell all of you on it because that's why we're here, but this is a timeline of every successful soft touchdown on the lunar surface. And in all of human history, the total number of successful touchdowns is 21, which is not that many, right? I think a lot of us, especially people around my age, which I won't disclose, but I'm not that old. There's a sense, I think, that Apollo is like been there, done that. We went to the moon. How hard could it be? But it's still very, very hard, right? And we have a lot of a string of 3 recent. Unfortunately, unsuccessful missions that remind us that it still is very hard. But hopefully those are, while we would have much preferred for them to be successful in sending back valuable science data that we can feed into our proving grounds, they are still valuable as lessons learned to potentially inform, what types of terrestrial testing may have been, the key to averting catastrophe in those missions. Those are the 3 pictures down the bottom. The Vikram and Bereshit landers in 2019, and then most recently the Hokuto-R just earlier this year. The other thing you'll notice, the map is showing the positions of all those successful landings, and there's nothing at the poles. We've never been there before. We've never returned samples from there. So we're going to completely alien territory and trying to emulate what the conditions are going to be like there. As an example, the closest was the Chang'e 4 mission, which is the only one that landed on the far side. But still, the distance from that location at about 45 degrees south latitude to the South Pole is, what is that on the slide? About 1,350 kilometers. So that's about the distance from here to Orlando. So difficult to draw reliable conclusions about the South Pole from all of our near side and far side missions. So I'll go through this real quick to try and save some time. This is just another justification for proving grounds, but this is specifically starting to look at communications and what are some of the benefits from a communications perspective that we get out of a proving ground. Well, we've got end-to-end link analysis, right? We can assess performance of the many interconnecting communications links. We expect to have a lot of different paths that data can take. We can go from an astronaut to a rover, back to HLS, back to Earth, up through a relay, back to Earth, up through different relays from different service providers back to Earth. There's a lot of different links that we want to assess end-to-end. There's also hardware T&E and V&E, so test and evaluation and verification and validation. Having a reliable proving ground allows us to place hardware in an accurately emulated environment for hardware test and evaluation and verification validation. Model refinement, this is one that's near and dear to my heart. We can compare our RF propagation models to the in situ performance data that we see as it starts coming back. And then we can use that to refine our models, develop new ones that may be more representative of specific lunar phenomena that we're seeing. Anomaly investigation, to put it kind of casually, we can basically create a realistic sandbox for tracking down any unknown anomalies or unexpected behavior, and mission planning. If we're confident in the results that we're getting from our proving ground, we can plan out specific traverses that are going to maximize coverage and data throughput. We can be confident that we can go into specific craters or permanently shadowed regions and still maintain coverage, despite not having line of sight in those conditions. So in terms of what kinds of features are advantageous for a proving ground, specifically for COM, number one, and I'm a propagation guy by background, so I'm a little bit biased here, but accurately characterizing that physical propagation channel is critical. So we expect a lot of site-to-site variation, and this is in terms of the lunar terrain, right? So it's the electrical characteristics of the regolith, dielectric constant and loss tangent. It's the depth of the regolith at any given location. What's beneath the regolith? The regolith is very transparent, so the scattering that's going on beneath the surface is very important. All those factors dictate how our communications links are going to perform. As a quick example, if you picture yourself on Connecting Ridge, and you're setting up a direct-to-Earth link back to Earth. You're obviously very close to the horizon because the South Pole, the Earth never rises above 7 or 8 degrees off the horizon. You will, from that perspective, be able to see the top of Malapert Massif, which is about 125 kilometers away. It's a very tall hill off in the distance, mountain. And that link over 125 kilometers is propagating across at least 6 distinct different geological regions on the terrain. So all of those are potentially different regolith depths, different regolith electrical characteristics, different clutter in terms of the rocks and boulders that are present in any given location. And all of that dictates what that propagation model is going to look like for your link. That's true for surface-to-surface links, and it's true for I'm doing bad on time. And it's true for all of our direct-to-Earth links since we have those very low elevation angles. Let's see. I'll add that most recently the Chang'e mission data has supported that with some comparisons from the different landing locations and showing the site-to-site variability along some of those parameters. Let's see. So just in the interest of moving quickly, I'll talk about some of the RF simulation. So in addition to understanding those regolith parameters, we also want to be able to accurately simulate that in terms of electromagnetics. This is an example here showing an ideal antenna dipole simulated in free space, how that's affected when you now install the dipole on a vehicle such as a lunar rover. You can see we still have a fairly omnidirectional pattern, but it's starting to get distorted by the vehicle geometry. And then lastly, when we actually put that in a realistic environment over the big ground plane over the regolith, the ground plane is getting pretty distorted. And that's, that can have a pretty significant impact on your link depending on the relative geometry of your lander and whatever it's trying to talk to. Being able to simulate that in a time dynamic sense is also very important. This is just an example of that rover driving past a boulder, and you can see the effect on the pattern, not only in the direction of the boulder, but also the pattern as a whole, because all that energy that gets reflected off the boulder has to go somewhere, right? And that affects the multipath conditions in the other directions. Same thing for the far field radiation pattern for a direct-to-Earth link. This is just an example showing that for an example similar to that first one that I mentioned from Connecting Ridge to Earth, looking over Malapert Massif, all of this is a function of frequency in your antenna design. But in this particular worst case kind of scenario, we're showing a fade of up to 16.5 dB, which is pretty bad. So you want to be able to predict that pretty accurately. And in some cases, it makes sense to, if you're going to see a multipath fade that serious, you may want to just change your operations a little bit, install the antenna in a slightly different place or off point a little bit. Being able to predict those things and reliably model them is key. So lastly, I'll wrap up here just talking about some of the development we're doing at Glenn Research Center in a proving ground-like capability. We have a new aerospace communications facility, which is pictured down there in the bottom corner. Just finished construction this year, and we're in the process of opening up a lot of the labs. We have a large near-field planar antenna range, compact range, and a spherical range, and lots of other good stuff. And of course, the modeling and simulation capability that you've seen a lot of already here in the slides. So this is a block diagram of the emulation environment that we're currently building and how we factor, like you saw in the slides, the simulations of antenna performance, the electrical environment, and the characteristics of the regolith into a channel model with the terrain data and the time dynamic, orbital dynamics and everything, and then bake that into a channel emulator that we can connect real hardware to. So I will forego the concluding remarks since it's basically just reiterating what I've already said and pass it over to the next speaker. Thanks.
So I'm Astroport Space Technologies. We were about a 3-year-old startup that began to look at the problem of how do we actually build on the moon. And our focus is going to be on, when we began the company, to focus it on lunar infrastructure, and in particular, landing pad construction. So what we do is we build infrastructure for the moon. Now, I was asked for the panel to answer this question, what are the elements of lunar architect and prototyping that we've done so far that's going to require validation and verification in a terrestrial lunar proving grounds? So I presented this at the last fall LSIC meeting. What we're focused on is making bricks. Now, there's all kinds of ways you could do construction in different materials. You could do cementitious materials for the pads or other sort of sintering technologies. But we decided to look at the very low-hanging fruit of just melting the regolith. How do you melt the regolith to turn it into a durable, hardened material? And we've been able to show that we can do it. We have just received our patent. It's not patent pending anymore. We got the patent for our nozzle. We call it an induction furnace nozzle that actually can take the feedstock, melt the feedstock, the regolith essentially, the regolith fines, form the pattern with the brick pattern, and place it all at the same time. And we're continuing to develop that. We have just recently received some funding for the second generation of this nozzle to improve it and actually show that how we can integrate it into a technology demonstrator. This is what we call our Lunatron system. This is conceptual at this point in time. The idea is to put this nozzle onto a mobility platform and use it for the actual construction of the pad itself in the operational phase, which is many, many years down the road before we get there. We've got to get to a technology demonstration phase to show that we can actually prove that we can actually make bricks on the moon. This is our test setup for making the bricks in vacuum, which is a challenge. The bricks I showed you in the previous slides were made in ambient. That's not, we've been able to get that down pretty good. but now getting this stuff to, and the harden and durability and the strength that we're able to obtain in the ambient environment, it's not the same in the vacuum, and we're still trying to break that code. We've been able to make bricks in vacuum, but they're not as durable as what we find in ambient. So this is the test facility. It's not a proving ground. We're going to need at some point a larger vacuum to put in our mobility platform and the integrated nozzle and this is an example of one at JSC. At some point, we're going to probably tap into this facility. The reason is, again, we're looking at our next step is to do our technology demonstration. So we're working on the terrestrial robot, not the flight unit, but the terrestrial robot that is going to be integrated with the nozzle and in a way to scoop up the regolith so that it can make a series of bricks in our tech demonstrator on the lunar surface, which would be delivered by a CLIPS lander. Again, we have additional funding for that to start doing that integration, looking at the hopper that's required for that and the feed system. We've gotten to the point where we've done some work with the razor drum excavator concept. And on the left side, you see the robot that we're going to use to do the terrestrial version of it. On the right is the flight unit that we think we're going to be able to construct. This is a lightweight material that we're working with a company called Gradell and our university partner to use a topology optimization of the mass structure so we can get the weight down. Just this played out a little bit here. Essentially, so that's essentially what we're doing here is integrating all the systems into one technology demonstrator. This is not the system we would use to make the actual landing pads. Again, this is to show that we can make bricks on the moon. Those two drums are scoopers, they're not diggers. They would be used to acquire enough regolith to make 4 or 5 bricks, a brick pattern. And the second one would be the backup system, or if we fail on the first run, we can have another drum of regolith. It's just to minimize the actuation we need to have for that technology demonstration. So our roadmap is to get to the surface by 2027 with the technology demonstration. I have here 2030 as the operational system. It's probably going to be further than that before we get to really making large infrastructure construction projects on the lunar surface. But we're on the roadmap. We're right now at trying to get our technology lunar terrain test bed built and to start developing the brick bot. The other thing we're working on, also funded through some NASA SBR work, STTR work, is the site preparation and construction topics. How do you actually do the civil engineering, the geotechnical engineering to do this construction, the site leveling of these sites, and what are the machinery that we need to have, and all those power requirements. And this is a location that we actually focused on, a specific location on the lunar surface up at Shackleton Crater. It's on the Gerlach Ridge area. We did some studies, and we did also some independent studies also verified this Gerlach Ridge location. The issue there is that it's very hard to find a flat spot. And when we even find in the flat spot, any variation in the location gives you a different leveling that you need to deal with, leveling of how much regolith needs to be excavated so that you can get a flat surface. We also have to deal with the layout, site layout, and all the roads that need to be cut for the first landing location away from where you're going to build the pad. And then you have a spoils pit or a borrow pit, depending on whether you're cutting into the ground or you're surface leveling. Where your location is for the power system, how that gets set up is one of the first things you got to do when you land with that first rocket and all your equipment. You have to offload it, and you got to stage. You got to stage and put your power system up first, and then your comm system. So these are all different locations in terms of the assessment, how far we can get away, and also how tight we can get it, so we're not moving too much dirt in terms of the cuts of the roads we need to build to go back and forth here. And then also dealing with the topology. And then goes the CONOPS itself. What's all the complement of equipment, and what's the scenario that goes into the setup. And we're talking about all the different type of tools that are going to be required, the spares, the charging station, the batteries, all this has to come into play in terms of the understanding these CONOPS. The message here, though, is that it's going to be a formidable task when we start talking about linear construction. We're talking about tons and tons of regolith. Here's some examples of what we think we're moving about in this particular scenario. Anywhere from 30,000 to almost 50,000 metric tons of regolith. If you can see them on the screen here, there's the two little dots in between the cones there. That's a 95th percentile human being. So it gives you a sense of scale of how much dirt's going to have to be moved around with these. And the problem is we're working with smaller drums. We can't do big bulldozer type of excavation because of the weight requirements or constraints. So we're going to have more of a fleet of these things, digging smaller amounts of regolith and moving it around. So all that's going to be tested out, right, in the test bed. Part of what we're also looking at is developing here is the excavation tools themselves. We're working with we have our strategic partner, Astrolab, as our mobility platform provider, but we're providing the tools that go onto these attachments for the robot. We have a couple other partners. 4Point is a Polish company that's going to be our partner in the conveyance. After it's been excavated, the soil's got to be moved to a sorting station and filtering station. We have a partner in Australia that's dealing with some of the compaction requirements. And then, as I mentioned, also Astrolab is our mobility platform provider. Now, how do we get to the point where we actually have a proving grounds developed? So Astroport is actually looking at building its own capability for proving grounds. We're located at San Antonio at the location called Port San Antonio. They're a partner in this endeavor. They actually have their own plans to modify it's an old air base. Kelly Air Base is looking to be turned into a technology park. That's a part of the BRAC closure that happened some time back. It's now become very successful and attracting new aerospace companies. Boeing and Grumman and all the big companies are all there as well. Their vision is to turn it from that previous slide to something like this, where they're really going to turn it into a high technology magnet area for companies to come and develop not just space technologies, but all high types of things. One of the buildings that's been promised to us is a space research and technology lunar terrain testing facility. This is currently into the requirements phase, where we will have not just the lunar terrain test bed, but also a research facility itself. Within the terrain, within the testing facility for the lunar terrain, we're talking about 20 meters controlled environment test facility for subscale testing of the robots at this point in time. Again, it's a joint effort between the University of Texas at San Antonio and the Port Authority. Currently, we're in the requirements definition phase. The fundamental goals of the facility is not just a research facility, but we want it to be a STEM education facility. So it's going to attract the community, student body to come there and see what's going on. And there's a museum next door to it. And there's also a public education venue for getting the community involved and making them aware of what's going on at the port and essentially the goals for our exploration of the moon. The problem, though, is that we're fourth in line for the building. They've already built the tech port, Boeing Tech Port. It's a venue that houses that can contain 3,000 people or personnel to hear concerts and all kinds of community events. On the other side of it is a museum that houses the technologies that are being developed on the port. That's completed last year. They're now off to their second building, which is a new office tower. And then the third building is going to be the vertiport. So we're fourth in line. So that means we're not going to have this facility until in the test bed until 4 or 5 years from now. We can't wait that long as a commercial company. So we're looking at building an interim solution that we can I think we'll be able to get this started probably towards the end of this year. We're going to have an outdoor facility. It's a lunar terrain test yard that's going to be using a simulant that we have. It's our own simulant we've developed called LCATS-1. It's a geotechnical simulant. It's not chemically analogous to the lunar surface, but it's geotechnically, mechanically analogous, and it's good for testing out with the vehicles and the movement of outdoor applications. Probably about 200 tons of regolith will be required to fill it up. It's going to be about, I think we have here, well, those are just the partners involved in it. It says 60-meter diameter. It's actually going to be 65-meter diameter, which is about a 100th scale of what we're talking about on the lunar surface. We're looking at a 2-kilometer area of activity zones and probably about 330, I think, 330 by 330 area of the actual landing pad area itself. So anyway, it's subscale to 100th of the scale that's on the lunar surface. We'll have a fabric canopy on top of it. Here's just a picture of what we'll be able to show, various scaled robots that we're working on. They'll be fenced in so for privacy and, you know, and IP protection from customers and our own IP. There's just images here of what this thing looks like in a view. There'll also be a command center. So we have a partner, our partner in Australia is adept at remote control in the mining industry, and we'll be controlling the robots from Australia with our partner there as one of the applications we'll be able to test out. You can see here that we can accommodate up to full scale. The robot in the back's the flex rover, down to subscale, and again even down to a micro scale with the 1/100th layout of the lunar terrain landing pad area. This is an alternative concept for the canopy. So the proving ground evolution for us, there's going to be not just one proving ground, of course. There's going to be a network of proving grounds and different scales for different applications as you advance the technology development. You know, everywhere from a micro scale where you can have these small robots doing a controlled environment type of thing and lighting effects that you can be able to control, to some more tabletop, smaller 20 by 20, which are typically what you find now in universities, to our subscale facility. Then eventually the controlled environment one is going to be at full scale, be important. ESA has one already that's going to be ready to come online pretty soon called the Lunar Facility. And then we have to get down to the point where we go into the outdoors part of it, when we start going full scale outdoor control. You know, how we get to that it's still TBD. We have some, we're doing site selections right now. We have two different sites we're looking at, one locally there and one in a location called Elpet, Midland, Texas, where the spaceport is at, Midland Spaceport area. But trying to determine these, it's what those requirements are at the point in time that you need it. Right now, we don't need those right now. We're not even close to that need. We're still at the subscale. We're still understanding how these robots move in the regolith. And now I'm worried about right now whether the regolith is the exact replication of what we find. I just want to see if the robots can do what they say they're going to, the operational constraint they're going to be working under as well. More about the ConOps for me and developing it for the digital terrain, the digital twin that we want to develop. We also have our partnership with, again, as I mentioned, in Australia is another location where we can have a command control center for remote control of the robots. One last slide. So, good time in there, all right. So here we are. This is our network of partnerships and our access to lunar terrain test beds that we have. We are located also in Luxembourg. I mentioned Australia, and then the locations in the U.S. States. Thank you very much.
Good afternoon, everybody in the room and everybody online. I hope you're hearing this okay online and that you're having a good experience. I've been on both sides. So my name is Rob Mueller. I'm a senior technologist and principal investigator at the NASA Kennedy Space Center. I'm the co-founder of the SwampWorks and the Granular Mechanics and Regolith Operations Lab. The kind of work we do is regolith-related, surface systems related, and mainly robotics for surface systems for excavation and construction. So it's very much aligned with what Paul and Sam are doing, and I resonate strongly with everything they said because it's absolutely true. I do want to talk a little bit about my experience in this domain because I think it's relevant. I have been part of the Desert Rats field tests in the 2007 to 2012 timeframe. We had the Desert Rats field tests at Black Point Lava Flow in Arizona, Meteor Crater, Arizona, Cinder Lakes in Arizona. We went to Moses Lake one year. I also have been to Hawaii on field tests. I didn't list that. And I was a navigator in delivering that yellow Humvee you see to Devon Island in the Arctic. And I had a really profound experience on that mission. So that was informed the thinking and my comments here. I've been part of the NASA geology field training in Los Alamos in New Mexico. The geologists came to us and said, well, you know, you engineers, you just don't get it. You don't understand geology. So we're going to take you out in the field and show you how to do some geology. So I did that for a week, and it was very educational. In my private life, I'm an explorer, an adventurer, just at heart, and I spent a lot of time in the Mojave Desert camping and on private expeditions, Rocky Mountains, and I own a blue water sailing boat, and I go out into the Atlantic Ocean and to the Bahamas and that kind of thing. So I have a lot of experience on just expeditions in general. So based on that, I think lunar proving grounds is a term that we need to explore in this workshop. I think it's more of a lunar proving capability in a series of lunar proving environments. And if we're saying proving, what are we proving? And even though I'm a technologist and I like to work on robots and develop construction and excavation robots, it's a little bit myopic. What we're really trying to prove is mission success. So I'd like to speak in terms of a more holistic approach, a mission success approach. And I think we're all a little bit guilty of being technologists, but mission success is more than technology. And in order to experience mission success and understand what it takes to have mission success, which is really what we're trying to prove here, a proving ground is to prove that we can do the mission successfully. So in order to do that, you have to go on a mission. In the expeditions I've been on, I'll just give you some key takeaways that hit me while I'm out in the field. First of all, topography. This is an actual picture, and a previous speaker commented on this with the topography and the high mountains. There's a cultural bias in us from the Apollo missions that we think the moon is flat. We think it's really flat and really sunny. And our previous speakers showed you that it's not sunny, it's full of moving shadows that are kilometers long, and it's not flat. At the South Pole and North Pole, we have a completely different environment than in the Mare. The reason they landed on the Mare in the equatorial regions was because it was easy to land on. It was flat and had good lighting conditions. So we're doing something tougher here. We're going to the poles, to the South Pole. This topography is extreme. This is a real picture of the South Pole Aitken Basin on the edge of it. It's one of the 13 Artemis landing sites. Where are we going to land on this? Sam just told us it's hard to find a flat spot. How are we going to do this? Scale. This is a picture of me standing in a canyon on Devon Island that just blew me away. This is really, it hits you. You know, you're nothing. As a small human being in this giant nature topography, you are nothing. How am I going to get across this canyon? And that was my task as the navigator, was cross this canyon. So Mission Control had the orbital data, and the orbital data was not very good resolution, so they didn't see this canyon. So they told me, navigate across this canyon. I radioed back to Mission Control. I said, Mission Control, who was in Houston, and I was up in the Arctic. I said, Mission Control, there's a canyon in the way. We can't get there. Oh, they said, oh, sorry, we didn't see that on the orbital data. We didn't know there was a canyon there. So, well, what do you want us to do? Oh, we'll get back to you. And then they got back to us and said, it's a 3-day detour around this canyon. Okay, that affects your mission. So scale matters. How much dirt you're gonna move, how much regolith you're gonna move. Scale matters. So keep in mind, scale is very, very important. Risk. We got into a lunchtime discussion, and I was trying to explain that when you're on a mission, your mind changes. Your thinking accelerates. You have a clarity of vision based on a very simple variable. Do I live or do I die? That's what your decision is based on. The week after I left Devon Island, there was an airplane crash at the airport that I landed at and took off from. This plane crashed, and almost everybody on board died. It was a very similar airplane to the one that I landed on. It was the same airport, the same flight traffic control. You know, everything was the same. This airplane crashed. It was a foggy day. It hit the side of the hill. Everybody was killed. That could have been me. Risk is something that takes over almost everything when you're on a mission. You make risk management-based decisions, and they're not engineering decisions. They're based on risk to your life and to your equipment and to mission success. So risk is another important factor. Geotechnical properties. If you try to drive a rover on this sand dune here, you're not going to do very well, because the geotechnical properties are completely different than you would find here on Earth, or, I mean, this is on Earth, but on the moon we're going to have different geotechnical properties. On the edges of craters, the regolith is soft. It's younger regolith, and it'll be harder to drive there. We have to pay attention to geotechnical properties. I drove for 16 hours across this terrain, and this picture doesn't really do it justice. These are called pingos. Pingos are permafrost features in the Arctic, and all I'll say is it's like driving over moguls on a ski field all day long in a Humvee, and you feel like a frog in a blender, you know. That's just shakes you around, and after a while you get used to it, but it matters, you know, to your driving. And finally, I've spent a lot of time in the Mojave Desert, and it can kill you. It can kill you very easily, and it sneaks up on you. Dehydration sneaks up on you, and before you know it, you're dead. There was a boy killed in Texas just last month in the Big Bend National Park. He was dehydrated, he died. And especially with all this extreme weather we're experiencing right now, the heat waves, this is real. We need to pay attention to it. The question we were asked on the panel was, what capabilities and features does the Proving Ground need to possess? So I'll tell you, it's very basic. When you go out into the field, the first thing you need is power. You're not going to survive without power. Power, water, and food and shelter. Those are like the 4 basic needs that you have. And if you don't have those, it's going to be really tough. Sanitation, it sounds trivial and people don't want to talk about it, but if you get dysentery or some disease while you're up there, it's not good. Wireless communication, we had a great presentation on communications. If you don't have communications, you're dead. Access, first of all, you have to get to your test site, and then you have to get around your test site, local transportation. Security, some of these places are still the Wild West out in the Mojave. You know, if you want to call 911, it takes maybe 6 to 8 hours for 911 to respond, if they respond at all. So emergency response and safety and security are not to be overlooked. But then the other thing we want to do here is definitions. And so I started thinking about this, and it was really confusing. Proving ground. Well, right away I think of Aberdeen Proving Ground. You know, that's a military proving ground. That's what a proving ground is. They test vehicles, you know, on different conditions. But is that really what we're talking about? And what's an analog test site? The expeditions that I just talked about went to analog test sites. And what's a test facility? What's a dirty vacuum chamber? How does all that fit into proving ground in the context of what we're talking about here? So in trying to wrestle this down, this is 2023. I used ChatGPT. And ChatGPT told me. It told me what a proving ground is. It told me a proving ground is a controlled and secured facility used for testing and evaluating various types of equipment, vehicles, weapons, and other technologies. It is typically an isolated area specifically designed to simulate real-world conditions and environments in order to assess the performance, reliability, and safety. There you go. We're done. That's a proving ground. Okay? But then I said, well, what's an analog test site? Well, analog test sites for space serve as terrestrial environments that closely resemble certain aspects of extraterrestrial conditions. So there's a nuance here. There's a nuance here between analog test sites and proving ground. And then a test facility is a specialized facility or laboratory where various tests and experiments related to space exploration, So you see, there's nuances. You can't just say proving ground because a proving ground has already been defined. It's already been defined what a proving ground is. So this community to come and say, we're doing proving ground, you're fighting all the previous definitions of proving ground. So I said to ChatGPT, say, okay, you just told me what a proving ground is. What's a space proving ground? The term space proving ground is not commonly used in the context of space exploration. Okay, there you go. We don't use it. It's new. However, it can be inferred to refer to a hypothetical conceptual facility that would serve as a controlled environment for testing and validating various technologies. That's pretty good. And so this term proving ground, I think, is problematic because it already exists. So we're trying to force fit a new definition into an existing definition. So I would like to propose that it's not a space proving ground, it's a space proving capability, and we're using proving environments, and that there's a hierarchy, and first you would go to a test facility, like a dirty vacuum chamber, raise your TRL 6, which is technology that works in a relevant environment. Then you have confidence that your technology works in a relevant environment, but you don't have confidence that it works in a relevant environment for long periods of time. So then you would go to the proving ground, or whatever we decide to call it. Maybe we do call it a proving ground, because that definition exists. And we put the hours on it in the proving ground. So now you have a technology at TRL 6, or whatever TRL you want. But let's say you're getting ready to go to the moon. Let's say it's TRL 6, but you don't have the hours on it. You go to the proving ground, you put the hours on it till it breaks. Then you fix it and you do it again until you have statistical models on what your spare strategy should be and what your repair strategy should be. Then once you've done that, you still haven't proven anything other than your technology. You still haven't proven mission success. So then you need to go to an analog test site and go on a mission. Then you have proven as best as you can mission success, and then you can go to the moon. So I put in for fun, I said, what is a lunar proving ground? And it told me a lunar proving ground refers to a specific location on the moon. So that's what a lunar proving ground is. Sorry, ChatGPT told me. So we have to figure that into it. Once you've been on an analog mission on Earth, which is the closest you can get to a lunar mission, then you actually have a lunar proving ground with a tech demo. We're flying the ISRU pilot excavator to the moon as a tech demo. We're not relying on it, we're just trying to prove the technology. So I would argue that's a lunar proving ground mission, is a tech demo to the moon. And we're doing that with CLIPS missions right now. So discuss. Thank you.
Okay, I think we're ready to move into our Q&A portion. So if anybody in the room has got any questions, go ahead and line up at the mic. I'm going to start with Slido. And I'll keep an eye out on the two mics to bounce over to the room discussions first. So I'll start with the highest rated question, but before we get into it, based on Rob's current discussion, let's set a ground rule for the first question. So let's assume that a lunar proving ground is the gap between what exists in facilities like TVAC chambers and the facilities we have in our lab and field test site, and that a lunar proving ground is distinct from those two things. The first question is that we can't simulate everything all at once, all together in one facility, right? So what are the major factors? What are the most valuable combination of factors that we are currently missing to be testing together? So I'm going to put that to any panelist who wants to jump in on the top couple, maybe 3 or 5, factors that we need to put together and test that would be our lunar proving ground. Yeah, if you've all got answers, go ahead. Go ahead, Paul.
All right, I guess I'll get started. Well, of course, I'm biased because of the kind of research I do, but the gap that I see is the large-scale regolith interaction, long distances, large quantities. So having a facility that can have large quantities of regolith that can be, made to whatever the test needs, in combination with things like gravity offloading and lighting. I think that's the thing that we can do really well in a facility. Other things would be a lot harder to integrate, I think.
So as part of the panel that I've been on, we traveled all over the NASA, and we looked at a lot of different kinds of simulations, including VR. We did look at some sample regolith ones that included lighting and simulated regolith. But the one piece that I really didn't see a lot of was gravity offload. There are some limited capabilities, like you can do a flight and offload gravity for 3 minutes or so, or you can use some cables, but then you're limited to two-dimensional movement. So I see the gravity offloading as being a big issue, because you want to drag something across the surface, you need to practice it at 1.6G. It's going to be a lot different than 1G.
Yeah, that's a good question. I think it was Paul who mentioned like a Lunar Proving Ground consortium, and then Bob kind of touched on that too. There definitely are a lot of disciplines where we need to be doing proving ground type activities, but I think that interconnectivity between everything is key, because there's not, the things that are valuable for one discipline to test, say communications, are if they're not at odds with what other disciplines want to test, they may not be synergistic in any way. So while it would be nice to have one nice gigantic chamber that works exactly like everything's going to work on the moon, if that's not physically impossible, it's definitely expensive, right? So I think it makes sense to focus on the aspects of what we want to test in a given test environment, and make sure that we can take those results. So for example, for testing communications in an anechoic chamber with regolith that maybe is electrically similar, we don't necessarily have to do the testing at the same time, but we can connect that data with another team who's doing testing of a rover that's moving through regolith that's mechanically similar to lunar regolith and has similar traction and characteristics like that. So I don't think we need to endeavor to do everything all at once, but endeavor to do everything and connect it all together.
So for me, the two big ones are the gravity environment. How are we going to simulate the gravity and vacuum? How do we make these systems work in vacuum? And maybe a third one could be also the virtual environment. How do we connect the virtual environment to the proving ground so that the physics are going to be the same in the two environments as well?
At NASA, we do mostly everything using systems engineering when it comes to missions. And this falls under the verification and validation part of systems engineering. So the process exists. At NASA, we're going to follow the systems engineering process. The chief engineer will review your equipment, your mission under systems engineering criteria. You'll either pass or fail the V&V. The V&V is a matrix, it's a test matrix. Test matrix has to address all the requirements. In this case, the requirements are unique lunar environment. So to me, it's just a big V&V matrix in the systems engineering process. Whatever your application is, you get out the matrix, and maybe that's what the lunar proving capability is. It's a big matrix of test capabilities, and you just check off for your system in the matrix. You go across the matrix, row by row, check off your requirements, check off the test capabilities that you've met, and that gets you through the V&V process. So I don't think it's a one-size-fits-all. I think it's a capability, a collection of capabilities, and in your V&V process, you check off what you did to verify your system, and then NASA will approve your flight.
Okay. This one is to Paul, and let's just touch on this a little bit. This open question about a consortium and what that actually means about who would run it and what that would mean for participation, right? I think that usually means you contribute some amount of money or resources into it, and it's a pool, and maybe briefly expand on that, because I think there's some interest in that.
Well, I would run it, of course, right? So, no, usually, other consortiums that already exist are usually collaborations between academia, industry, and government. And they typically, like Julie already mentioned, pool resources, but also knowledge. And typically it is governed by some sort of, board or management group who manages the resources specifically, because typically there's some facilities involved. And the other part of that is, of course, membership fees that sometimes get paid by commercial entities and things like that. So there has to be some sort of management organization set up. And depending on the size, this could be from representative of each of the different groups. So, but it could also be run by a specific host who starts it, and then things might grow from there. LSIC is kind of an outside group that does this thing for NASA. Maybe it could start there, and they could set up a board or something like that. There's different ways that this could be set up, but I think it would be very important to look at existing organizational structures already. This is not a new thing, it's just a new field. And so we could, in many ways, learn from what other people have already done in developing a new technology area and how to pool the resources so that they can leverage each other. Because that's, in the end, I think the most important part, is we don't duplicate efforts, we all learn together.
Okay. The next question's a little loaded, so I'm going to go back to the way I started. Okay, so we've got field tests, we've got test facilities like vacuum chambers, we've got whatever the Lunar Proving Ground is that fills some gap between them, and then there is the moon itself. So the question is, do we actually need proving grounds? Seems like we just want to create the moon on Earth, so why not just go to the moon? So, so this speaks to the demonstrations, right? Sending demonstration missions. So if any panelists would like to weigh in on the different factors, or, yeah, figured, Rob, go ahead.
So it's really simple. It's cost. If we're going to hopefully in LSIC identify all these capabilities, and then you'll do the highest fidelity testing you can afford. And if you still don't meet the mission criteria, you have to go find more money. But one of the attractions of a field test is you have vast amounts of terrain which are kind of random with appropriate geology. That's pretty cheap. You can't build that. Like all this moving regolith simulant, why move the regolith simulant? Go somewhere which has a geotechnical simulant that's similar to the moon. There are silt beds. That silt is very similar to lunar regolith. You could find a silt bed and avoid the cost of moving all that regolith simulant. So it's all cost related in my mind.
So yes, I think we would go to the moon, and we want to test a lot of stuff there once we get to the moon, but I think we are limited in how much we can send to the moon. And I think when we are on the moon, we want to test our improvements and continue to improve on all the things we do. And those go to this V&V process, which in my mind includes continuing to use all our test facilities. It's not that once we're on the moon, we're going to stop testing. At Michigan Tech, we have a 900-acre proving grounds, which literally 100 companies come every year to test their equipment, whether they are tires or full cars or trucks or even military vehicles. They get tested every year because there's improvements and changes they want to run through the systems. And so I think it's very similar here, where we are going to be testing continuously to improve on our systems, and we can't afford to do that on the moon with every idea or everything that we have. So we're going to need something on Earth where we can do continuous testing, basically.
And I'll jump in with that I think Jody's poll, our lunchtime poll, actually had that question about the need for a lunar proving ground once we're on the moon. So I'll be curious to see the results of that, because that relates directly to that question. I'm going to throw one to specific panelists here in between. So Michael, this one's for you. I'm going to broaden it a little bit. You talked a little bit about proving grounds and their use in communication, and that the ground regolith had an effect on dissipating the signal. What other elements might affect your communication, other factors that might affect your communication that a proving ground would need to have or simulate, other than perhaps a large distance? And then the specific question was regarding RF analysis, that the dust might impact the communications with the RF.
Yeah, both very good questions. So beyond just the characteristics of the regolith itself, I would say the next most important factor is really the communications architecture that you build, right? Not only in terms of UHF versus Wi-Fi versus 4G or 5G, but in terms of where are your base stations? Where are your antennas? Do you have something that's just built onto the side of your lander? Do you have something that astronauts can take out as cargo and deploy somewhere to get better coverage as they go down into a crater? Do you have something that's maybe autonomous and self-lands and gets into position to provide coverage over an area before the crew even gets there? And I think the answer, hopefully, is a combination of all of those things, right? And obviously, beyond just the surface, we need to rely on a network of orbital relays to make sure that we can have coverage back to Earth when we don't have direct line of sight to Earth, which from the South Pole is at least half the time, right? So I think that's another very important aspect to consider in the proving grounds. And then the second part of the question was?
RF.
The dust, right? So another key consideration, and I put on my slides, unfortunately, and I don't think I even got to it. But one of the factors that we're considering in our RF modeling is the potential for electrostatically lofted dust. So the lunar surface environment is very alien. It's directly exposed to the solar radiation. And the current understanding is that dust particles, which can become charged, can also loft into the air through electrostatic forces as they're exposed to that solar weather. So not only do we have dust clouds that get kicked up by astronauts and vehicles moving around, we also have dust that just levitates itself and hangs there as a cloud of dusty plasma, which is also not a fun thing to propagate through, but another thing that we need to understand and model appropriately in a proving ground.
Okay, I'm going to do another specific one. Miranda, this one's for you. This is regarding, oh shoot, I just lost it. It was regarding models for lighting conditions, and if they're open source, what open source models or software toolkits might exist for lighting conditions. Can we use those? What facility gaps exist for lighting conditions? That sort of thing. So what do we have in software and in physical?
So I don't know of any. Well, we have software in terms of simulations, but the problem with a lot of the simulations is you can simulate, for example, how long it takes your eyes to adapt with the VR, but we haven't been able to simulate glare, and that's been a real challenge to be able to simulate the glare that you'll experience. And the other we did see a lot of analog models, so there are some good lighting labs. There's one at JSC, which is good. There's one that we saw up at Ames that was good. But it is hard to capture the depth perception, I think, would be the way to put it, because the sun is going to be further away than you can really experience here. So that's something we haven't really resolved yet either.
Okay, and there's a whole bunch of new questions, so if you're not following Slido, jump on and rate them up if you like them. So this is to whoever on the panel wants to weigh in on this. So this is a question about tribocharging and dust adhesion, which are very important, of course, and the vacuum behavior will change, and as well as with radiation. Are these part of an LPG, or how would these be a part of an LPG, especially a large system, or is this something that's more facility scale, or how do you view this higher level of dust interactions, specifically adhesion and charging, as being part of a LPG model? Michael.
I'll jump in real quick just to say that from a communication standpoint, you've definitely got dust that accumulates on your antennas, and that becomes a factor in how much signal you're able to receive from those antennas. And that's certainly something that gets worse the longer that infrastructure is going to be in place, right? So for a very short sortie like Apollo, not really a huge concern, but for something that's going to fly and be up there for 10 years, that dust is going to get pretty serious pretty quick. And if we don't have a way to clean it off manually or through some electrostatic repulsion or something, we certainly need ways to mitigate the impact that it has, not only on antennas, but on the gimbals that steer our antennas around, if it's getting into the mechanisms, and there's all kinds of considerations there. I think that's one of the biggest challenges.
Go ahead.
Yeah. One thing to add here is that when we're talking about testing at scale, simulating the properties of charging is, well, I'm just going to say impossible, because the simulant that we're going to use, just for cost and production reasons, is not going to be necessarily accurate enough to properly simulate those kinds of properties. Not to mention we'll be in an atmosphere for most of the time, and so that is a property that I think we simply cannot test at a really large scale, and that's something that we can test in small scale, in small facilities, test sites, and then in the end, hopefully model with those kinds of properties we measure at smaller scale. Hopefully that will be sufficient, and then at the moon's surface, we'll have to do the actual test and monitor how the actual degradation and stuff would work, because that's a property I don't think we can model cost effectively at scale, at a large Lunar Proving Ground scale, I mean.
Okay, question for Sam. Are you planning on creating a full-scale analog for high-priority site outdoors, as folks did for the Apollo mission? So how big are you planning to go with that? And then there's also a question regarding your simulant and if it's available for other users.
Well, the answer is yes, but not right away. It's going to be sometime in the future before you even get to that point. As I think I mentioned, we're going to go do subscale testing first of our robots. And we have actually started identifying a couple of sites for large-scale outdoor testing as well.
I think
way down the road.
The question was for a high-priority site. I think they're saying maybe mimicking a lunar site specifically, as they did for the Apollo missions. But yeah, I think the answer is still the same, I think.
Yes, it is, yeah. And I don't think we would try to replicate a lunar site in an outdoor facility.
You wouldn't?
Would not.
Would not.
Yeah. What we would do is replicate the conditions of a particular site, but not a whole full-blown replication.
I like that one, but I don't know that the answer is who's writing the testing requirements for the LPG. I think we are right now.
It depends on the user, I would think.
It depends on the user. That's true. What considerations have been given to operational and observational differences between Apollo sites versus the 50-meter tall Artemis lander, and how do you think that affects our testing capabilities? Any thoughts on that one?
From a visual perspective, you know, the lander will offer huge, long shadows, so even when you're in sunlight, you'll have to deal with the transition between the shadows in that we're in the working area of the lander versus the bright light of the sun. So it will drive some, maybe perhaps some lights, perhaps some kind of a modeling design, but the lander will probably have to participate in that somehow. So you'll have to look at the integrated system.
And Rob?
One of the big differences is just that the Starship is so much bigger than the Apollo M was, 100 metric ton payload to the surface. So the plume effects are unknown at this point of the interaction of the rocket engine with the surface of the moon. In Apollo, we did see Regulus was ejected, and it's going to be ejected at velocities of 2,000 to 3,000 meters per second, and so we need to figure this out unless we have a landing pad. If we have a landing pad, then the issue is solved. But if we don't have a landing pad, then we have to understand this. So in response to this, SpaceX has moved the thrusters from the aft end of the Starship to the nose cone, and they're trying to mitigate it that way. But the jury's still out on what those effects will be, and I think that's fine in the first few missions, but the more assets you aggregate around the lander, then the more susceptible you are to plume impingement.
Yeah, sorry. So in our lunar surface studies, we trying to assess the complement of equipment that needs to be brought on the first mission, the first landing mission, where there's no pad and land on the unimproved surfaces. And you have to offload all that equipment, and it's, you know, if we're talking about a Starship, we're talking almost 100 tons of equipment, or less, or somewhere in that capacity. And all that equipment's got to be moved out of the way for when, because it's not going to stay there, the Starship is going to go back. It's a valuable asset. And we have to find either natural or terrain to hide it from, or move it far enough away so we don't get that, you know, that takeoff, you know, blasting away our in-placed assets as well. So that's a problem, actually, because it puts into the timeline how you deal with this as well. Do we put that, you know, begin the construction right away, or do we have to take the time to move to some distance away from when that lander takes off as well? Or we would prefer the Starship to stay there while we're doing the construction. And that's probably not in the feasible realm.
I'll just add that, you know, the higher you can get an antenna, the better for coverage, obviously. You know, you've all seen the cell towers, and they're at an optimal height for covering a given region. So from that perspective, a 50-meter tall Starship is pretty appealing, that your lander is basically its own cell tower, potentially. But it's got some challenges too, right? Because then you're limited to where it lands. You're also limited to the fact that it's only there when crew are there. So if it leaves, then you're not necessarily supporting any robotic missions with those assets. And we also, you know, expect to have an environment where we've got different vendors for different missions, right? We know now that Artemis 3 is going to be Starship, so is Artemis 4, and then Artemis 5 is going to be Blue Origin, right? And we don't necessarily want to have different capabilities. You know, from a comm perspective, we don't want to have our range dictated necessarily by the specific lander. So it's another challenge to work around in terms of how that communications architecture gets developed while still taking advantage of that, you know, massive height on the lunar surface when we can get it.
I think we're out of time. I would say with all that discussion and what was offered here, I think we do need to address the idea of scale, because I'm hearing some very big scales here on testing and maybe what we really need or mean when we're talking about a controlled environment and how big does it need to be. So thank you for the panelists. Let's everybody give them a round of applause. thank you for all those who offered great questions on Slido and rated those up. So Jody?
Yeah, and let's thank Julie for being an incredible moderator. And yeah, there were tons of questions on Slido, so thanks to everyone for putting those in. And for the ones that are remaining, I think what we might do is, collect them. We're going to archive them, collect them, and then maybe send them out to the panelists. And, at will, you guys could respond to them through email, and then we'll make sure that everyone in the community has access to those, if that's okay.